Okay, so let's start. I think so far quite a bit answer. So I think I said that basically what we are doing is that we are taking machine learning, right? And then we are taking embedded systems, and then we want to run some machine learning algorithms on an embedded system, right? And then once we are doing that, it means that you're going to have some challenges because because machine learning is mostly run on TPUs, GPUs, and CPUs. But now we want to run machine learning on embedded devices like the microcontroller. So there's obviously going to be some kind of challenges as compared to in case you are running it on GPUs, TPUs, and CPUs, right? So we know that we already know the building blocks of the computing system, right? We have the hardware and then we have what software, right? Everybody knows this already, right? And then if you talk about the hardware, I said before that the hardware consists of a compute, right? It consists of memory, and then it consists of storage. Then we know the difference between memory and storage. We know that, right?
Yes, yes. Something.
So the difference is that in terms of memory, memory is like your short-term memory, right? Now, in terms of memory, yeah, memory is like short-term memory, right? So if you power off your device, everything within that memory goes off, and then once you power it on again, all the information is lost. But with the storage, the storage is like your hard disk, right? You know that once you write something onto your hard disk on your
Yes,
PC and
forever.
then you power it off,
Yeah.
it still what retains it, right? So this is what a computer system is made up of: compute, memory, and storage, right? So now, and then we went through, like, I think we talked about the difference between a microprocessor and then a microcontroller. We know that already, right? And then I said that for a computing system, you have a microprocessor, and then we have a read-only memory, write-only memory, some I/O ports, timers, and stuff like that. All of these are single chips. The microprocessor here is a single chip. The read-only memory is a single chip, right? Everything comes together to make up the computing system,
Okay.
right? So the microprocessor is just one part of a computing system, right? So if you take a microcontroller, I said that it's made up of the same things as a computing system, but it's just that all those things, the CPU, the read-only memory, write-only memory, I/O ports, all come together into a single chip, right? That is what we call a microcontroller. So here you see that we have memory is a single chip, the RAM is a single chip, the CPU is a single chip. Once you're able to combine all this into one chip, like this one, right? We call that a microcontroller. Easy, right?
Yeah, very easy.
So then I think we are going through this already, and then we said that the heart of the computing system is what,
Microprocessor.
and the heart of the embedded systems is what,
Microcontroller. So
right?
we've not discussed this and got it there.
And I think I made mention of it some time ago, right? So and then we know that the size of most computer systems are actually large, right? And then for that of a microcontroller, they are just small. And then we know that the microprocessor is more flexible than the microcontroller. Do you know that? No.
So again,
The microprocessor is more flexible.
yes, because these are using the controller are using embedded system. They are programmed for a
A
specific
specific task.
task.
So they are actually limited. But for the microprocessors, they're using a computer system that can run a lot of things, like your CPU, like this, right? The CPU on your PC, right? It can run Word, it can run what? Any app you give it, any application you design for it, it can run a lot of stuff, right? So it's more flexible than the microcontroller. Understood?
Yes, sir.
Yeah, so for here, for an example of microprocessor is your general purpose laptops, your the servers, right? Your desktops. Then an example of a microcontroller used in an embedded system is what? As I said, the aircon, right? Microwave, then
Washing
probably,
machine.
pardon? Washing machine, right? So you know that these ones are designed for just one specific task. But your CPU, the CPU on your machines, on your laptop, is designed for a general purpose kind of task, right? Okay.
He said, our remote for
TV remote.
fine, TV remote,
Mm.
can be TV remote, yeah, and embedded.
Yeah, it's been animated. It's made for some specific tasks. It can do a lot of different tasks. Only probably turn on the TV, change some channels and stuff like that, right?
Okay.
Any other question? Okay, so now let's put some kind of figures to the microcontroller and then the microprocessor. We know that for compute, in terms of frequency, right, or speed, you know that the microprocessor always has higher. Like your laptops, if you check your laptops, it runs from probably 1 gigahertz to about 4 gigahertz, right? Most laptops is about 2 point something, 2.1 gigahertz or something, right? But for the microcontroller, they run between 1 megahertz to 400 megahertz. So in terms of frequency, the microcontroller is very limiting. It can run for shorter speeds micro than the microprocessor, right? In terms of memory, right? You know that your normal CPUs have larger memories. Some have up to probably 1 terabyte and stuff like that, right? But for the microcontroller, the memory is just small, from 2 kilobytes to 5.2 what kilobytes. I
Megabyte.
mean, in terms of power, let's take power. You know that your machine runs on probably about 30 watts or something like that. But the microcontroller must run on from 150 microwatts to 23.5 milliwatts. So that's very, very small. So it means that once we are trying to run some kind of machine learning or stuff like that on a microcontroller, it's going to be really, really challenging because it lacks a lot of that resources. Right? So you see that everything here is lower than that of the microprocessor. So we need to do something extra
You
to be able
compress.
to
You
to be able
compress
to
the
yeah,
things.
to be able to run it on,
The
right?
microcontroller.
So, sir,
So first of all,
sorry, you said, when
uh,
it comes to the power, is
yeah.
that not an advantage over the microprocessor?
Hmm?
Is that not an advantage over the microprocessor when it
What
comes to
advantage?
power?
Uh, what's the
Power.
advantage? You mean that the microprocessor is more advantageous than the or
In
what?
terms of the power energy efficient than
You mean the microcontroller is more energy efficient? Yes, but once you want to run a machine learning algorithm, it has to consume a lot of power, right? So, for instance, if you have a battery, like most tiny machine learning devices run on batteries, and then if your machine learning algorithm consumes a lot of power, it means that your battery will be running down faster. But you know that when it comes to power with laptops, you're always connected to a power source, so you have no issue. Understood?
yes, sir.
So with these limitations, right, you in designing an algorithm or any algorithm at all, whether it's machine learning or not, you have to really consider how difficult the task is. Is the task very, very complex or simple, right? So it means that if it's very complex, then an embedded system is not your solution, probably, right? And then you need to consider how much memory the task is going to use. Now we saw that the memory on our device is actually very low. So if your task requires a lot of memory, probably this is not your option, right?
Yes, sir.
And then you need to also consider how long the algorithm will run for, right? So it means that if the algorithm runs for long, it's consuming more power. If it runs for less power, right? So if your algorithm you are designing is going to run for a long time, that means that probably this is not your solution, or you must find ways of making it efficient. If not, it will run the power down on your microcontrollers, right? So these are some of the limitations and what you must consider when you are designing your algorithms, right? Understood?
Yes, sir.
So these are some embedded boards, and then what we are using is the one in the second one, right? And then we have all seen it before. And then what we are using, uh, the clock frequency is 64 megahertz. The flash is 1 mega, and then it has some internal sensors like the IMU, temperature, humidity, gesture, pressure, proximity, and stuff like that. And then it also has an embedded Bluetooth, right? So you can connect your phone Bluetooth to the device, that small device, right? So this are some of the components on the device we're using. So now we know the limitation of the hardware,
Yeah.
right? We know that it's really, really limited when it comes to running machine or running any algorithm at all. Now let's talk about the software. So once we take a software, we know that the software is your applications on your probably your desktop or something like that, or your laptops. The applications on the laptop, right?
Yeah.
Are the software. But underneath the applications is a library. The library just helps you run the software, right? Now we know that we have hardware, which is the the chips on your laptops, right? Now, how does your application communicate?
Yes, sir. On the laptop.
So, how does your software communicate with the hardware? It needs some kind of interface, right?
Yes, sir.
That it will help you communicate with the hardware, right? So that interface is what we call the operating system. We all know that, right? The operating system helps your software communicate with the hardware effectively, right? So when we look at general laptops, we know that we have operating system like the Windows, right?
Yeah.
Then we have the Mac OS, and then we have the Linux, right? When we go to mobile phones, we know that there are mainly two of them. I don't know whether they are more. Are there more?
First, Nokia was there, but now you have
Nokia is
Android.
an operating system.
Nokia was using Windows.
Windows, yeah, yeah, yeah.
And now you
So they are using it.
no, now you
When you buy it, you get dual. You can change.
Ah,
It's Windows and Android.
okay. But generally, the point is that they're used to iOS or Android, right? Those are operating systems within the mobile devices. Now, when it comes to embedded devices like the one we are using, right, the Arduino Nano Sense, we have an issue here. You see that the the Windows OS, if you check your Windows OS, it mostly consumes about 20, 30 gigabytes, right? Or how big is your Windows operating system on your machine?
say how can I
Nah,
check?
I didn't say check anything. So you guys don't know how big your Windows is. It's about 20 to 30 gigabytes. Gigabytes. So it consumes that much space, right? About 20 to 30, yeah, between 20 and 30. So now we have an issue. When we come to embedded systems like your microcontroller, that in no sense, it has only 1 megabyte flash, only 1 megabyte. So so it means that it is impossible to put Windows or even iOS or Android on that devices. Now the point is that there are some kind of embedded OSs for those kind of devices, and then one of them is called the FreeRTOS, and then one of them is also called the ARM Embed OS. But then the issue is that you see that once you have this operating system running on it, it is taking space, and then we have only 1 megabyte of flash left. So it means that if you are designing an application that will use one of these OSs, it means that you have so little space left for your application to run. So in case you are designing need to control something, it means that the OS will take about these ones will take about probably 90% of it, and then you have only 10% left. So it is always advisable to use this kind of OSs on your microcontroller. So normally we run the microcontroller without any OS at all because we just want to control some kind of simple kind of devices. Once you upload this kind of OS on it, it takes about 90% of the space, and then you only have about 10% left, right? So that is a big issue. Understood?
Sema,
Now, huh?
if they are run without OS, and we know that the OS is the interface
Yeah, yeah,
between
yeah.
the hardware and the software. So in the embedded system, how are they going to?
Yeah, so the embedded system, once you are programming using the Arduino sketches, right, you are communicating with the hardware itself. If you run it, because you see that you write a code that, 10 pin 1 or pin 1 or pin 2, pin 3 on or off. You are communicating with the actual hardware. You don't really need an OS. So you yourself can communicate with the hardware directly. Unlike your PCs, you cannot communicate with your hardware unless you write some software. And that's what. Now, next is from the applications, we have the libraries. I said the libraries help you run the software, right? Yeah, if you look at, I think I talked about this NumPy library before, right?
Yes,
I said it does what? It helps with, eh?
arithmetic. Arrays and metrics.
Yeah, arrays, matrices. It helps, it, it makes it easy for you to manipulate arrays and matrices in Python programming. So this is a library, right? And then this library, this NumPy library can run on most CPUs, be it Windows, be it
Linux.
Mac, Linux. It can run on all of them. So it means that it has what is called, it is actually very what portable. It can run on all of this, right? So the libraries can run on Intel, it can run on iOS, Android, that kind of library can run on it. But in order to make a library very portable, right, it means that you need a lot of kind of drivers. So it means that the library must have drivers for the Android phones, it must have drivers for the Windows PC, it must have drivers for this. And then once you are adding drivers to it, you know that the size of the code is what? Increasing. So normally, if you say a code is portable, it's good, okay, but it means that that code.
Versions. Then our chairman is here. So now you can proceed with
Shall I continue?
Chairman, should we continue?
Sir, please, you can continue. Thank you.
Thank you, Chairman. Alright, so as I said, if the code is portable, it means that it's good. It can run on most operating systems, but most CPUs. But it means that the size of that code is actually huge, right? So running portable kind of libraries on microcontrollers is impossible. Understood? So now you can have some kind of options. Portability trade-off. So if you have a code that is highly portable, it means that the cost of that code is what is high. Simple, right? It's very portable. It can run on all systems. It means that the cost is high. It means that it consumes more power, right? It also means that we use a lot of engineering effort in order to make that library or that code, right? For a code to be portable, you need a lot of time to make sure that every component, all the drivers, all the libraries, like all of them come together, right? So that is the engineering effort. Understood?
yes, sir.
Now you can have a code with lower portability. Now, if a code has lower portability, it means that the cost is actually lower, right? So it means that the code can run on every system, but it can run on a particular device. So once you do that, you have removed a lot of drivers, a lot of libraries from it. So that the cost of that code becomes what? Cheaper, right? It becomes cheaper, and then it consumes less power, and then it uses less engineering effort. You don't have to do a lot of coding in order to make it work. Simple, right?
Yes, sir.
So now, in terms of our embedded systems, right, we want code that are less portable. but can run, on the embedded devices. That is our aim. So it means that we are using less power, less engineering effort, and then we are using less cost, right? So now, if you have, so it means that if you write a library or a code for an Arduino Uno, today is the Arduino Uno, right? You cannot go and run that code on, you know what a Raspberry Pi is? Raspberry Pi. It's some kind of board. That is used over there. This one. You see that it looks almost like the Arduino, but it's not an Arduino. So it means that if you write a library or a code for your Arduino Uno, you can't go and run it on the Raspberry Pi. So it means that your code is not portable, but your code is actually efficient enough to be run on only one device. Understood?
Yes, yes.
So, but with this, the opportunity, it means it's only for a specific
A specific device.
device. Go ahead and just
It can't. It can't run on other devices because you have not taken those other devices into consideration. Once you take other devices into consideration, your code becomes huge. Understood?
Yes, yes.
I, is it the environment that a code is written or compiled that specifies the hardware it can run on, or
Or what?
the size of the code?
Or now is so like I think when I was showing you how to run codes on your Arduino board, right? On this one, on on the board I brought, right?
Yeah.
I told you that you needed to download a specific library for that board alone.
Yeah.
That library is specific to that board, right? So it means that without that library, and then you writing codes for that library, the board cannot work,
Okay.
right? So it depends on the library you are using. So so each embedded device has its own library, completely different. So those code, if you write code for this Arduino board is this Arduino Uno board is an Arduino board. If I write a code for Arduino Uno board, because of the libraries I used and then the libraries I called on my code, that code cannot run on the Arduino Nano, the one I have. It can't run because of the libraries you are calling. The libraries have different functions, completely different, right?
So
Understood? But for instance, if you write a code like if you write a C code, right?
okay.
And then you compile your C code. You can go and run this C code on your Windows OS. You can go and run the C code on the what do you call it? Your Mac. You can go and run that C code on your Linux. That code is highly portable because they have libraries that considers the Mac, and then all the other CPUs on it. So that's why you can run that kind of code, a C code, C++, Java codes on any machine you want. But with this Arduino codes, you can't do that.
Okay.
Understood?
So they are hardware specific.
Yeah, have a specific. Any other question? Any other question? Right. So in in summary, right, embedded system is extremely limited in performance, power consumption, and an embedded system is not as portable and flexible as mainstream computing system. That's just what I talked about. Yeah.
Okay, so this is embedded hardware.
Yeah. Yeah. Right. So now we have looked at the hardware side, right, and then we have looked at the software, and then we have looked like that. And then I said that when we talk about tiny machine learning, we have the embedded system, and then we have what? The machine learning itself. So the machine learning itself is also an issue. Now, to run the machine learning itself on the embedded device, as I said, there's another issue because if the machine learning is very, very complex, it means that it is going to consume a lot of power. It's going to consume a lot of memory. So now we have an issue here. When you want to run it on a device like the one I have with only 1 MB flash, so that one to you is an issue. So now let's talk about the machine learning itself. And I said deep learning is a subset of it. Machine learning. The deep learning is mainly used for classification, right? You have an image of a cat or a dog, and then you pass it through your deep learning model, and then the model can tell you whether it's a cat or a dog. Easy. That's deep learning, right?
Yes, yes.
And then when we talk about deep learning, we said that deep learning uses what is called the neurons. And then I said that the neuron actually mimics the neuron in our bodies, in your body, in a biological system. The biological system has a neuron, and then that is it over there. If you study biology, probably you might have seen it before. How many of you have seen it before?
So this one is
In your biology course, you have seen it before, right? So this is just how it looks like within your body, right? The neuron within your body looks like it has inputs called the what? Dendrites. The inputs to the neuron in the dendrites. It has a cell body, axon, and it has outputs, right? So they looked at this one in order to design the neuron in machine learning. So the neuron in machine learning depicts what is in the bodies, right? So if we take just one neuron, right, one neuron has inputs, input one, input two, input three, and then it has an output, right? Now, what is very very important is that once you have an input one, input two, input three, each input has a parameter called the weight. We have a parameter called the weight. So we have weight one for input one. So each input has its own weight, right? Weight one, weight two, weight three, right? And then we have another parameter called the bias, the bias, B.
you are being biased.
So we have the weight, and then we have the bias. Now, what does all of this one mean? So you see that, as I said, it's machine learning, right? So it means that the neuron is learning. So if I want to classify whether an input image is a cat or a dog, right? I feed the image through a system like this. But they're just one neuron, they're just one neuron. I feed it through a system like this. So it means that the inputs to the image are the pixels. I talked about pixels the last time, right? Each image has pixels, right? Each image has pixels. So I feed these pixels through the system, right? And then the system will learn these values, the weight values, W1, W2, W3, and then the bias. So what does this mean? It means that for you to classify if an image is a dog, right? It doesn't consider the entire image, right? It means that, as I said, in machine learning, we are looking for specific patterns within the image that will tell me that this is a dog or this is a cat. And then we know that a dog and a cat are completely different, right? So it has some kind of features, right, that will tell you that it's a cat or a dog. So this input here, we have so many, we have so many pixels, right? We are feeding all of this through the input. Now, this weight will determine how important the pixel is. Understood? So, is this pixel important in determining if that image is a cat or a dog? So these are the weights. So the weight will now determine if the input is important or not. If it's not important, it means that the weight has a lesser value. If the weight has a lesser value like a zero, it means that this input is not really important at all in trying to identify whether it's a cat or a dog, right? If the weight is huge, right? If the weight is a huge number, it means that that input is very, very important in determining whether an image is a cat or a dog. Understood?
Yes, yes.
And then we have the bias value also. So it means that what what it does is that each neuron takes its input. It takes the input one and then it times it by the weight one, right? And then it takes input two and times it by weight two. And then it takes input three times weight three, right? So it sums all of this up, right? And then it adds the bias value, right? And then it passes this one through a function called the activation function. So it passes this, all of this, right, through a function. You pass it through some function, and then you get your output. So the output of the neuron is equal to this, the function, and then within the function, we have the input times the weight. You sum all of them up. Then you add the bias, right? So what is the activation function? What is this? What is it used? Now the activation function will actually limit the output, right? You don't want the output to go above some threshold. You are probably mostly you are limiting the values to 0 or 1, right? So if the value is between this number and this number, the activation function will say that, oh, let's compress that number to 0, or let's compress that number to 1. That's all it does. Understood?
Yes, sir. So what's the function of the bias?
The the bias will you know that if W1 is 0, W2 is 0, W3 is 0, so here becomes 0, here becomes 0, here becomes 0, and then everything becomes 0. So it means that your entire equation becomes 0. You don't always want that. So the bias is a constant. It's a kind of a constant that will help you not to make everything always 0. Right? So if everything is 0, but you know that the bias one sometimes you choose 1 or 2 or something like that, so that you will make your output 0. It, it just helps you. Understood?
Yes, sir.
Right.
So like someone who has written an exam, if you get zero, that's because he used
Aha,
like
people like
maybe you have to
they
give
just
zero.
want to boost you up. So, oh, just for coming to write the exam, okay, right? Just writing your name, give you some 5 marks.
Sir, please, the activation
Function,
function.
yeah.
Yeah, what's the abbreviation?
What's the what?
The abbreviation. What's the answer to?
And why is it?
Is it the same?
Oh yeah, this is the same. You know that.
Yes,
So
the left side of the
Out, she
equation.
wrote out.
this one, why?
No, no,
On
no,
the
the one
board.
written by the one you wrote by
On,
yourself.
on the board, on the board.
Yes, on the
Out,
left hand side.
out is equal to.
Output, yes, output. So this equation here is just the same as what I've written. So you will just sum the input is xi, and then the weight is wi. Just sum all of them up plus the bias, and then you pass it through the activation function, and then you get your output y. So these parameters are very important. W, I, and B are what we call the parameters in machine learning, and then that is what the machine, the algorithm learns. You give it an output, and it learns these values, and then you use these values to predict some patterns within an image or whatever you are doing, right? So these are how the next people like you can go and learn. You can go and learn them on your own. So there are different structures, but the most important thing here is that we are trying to do. We are trying to do something here.
Different. Affiliates different.
So let's look at the machine learning algorithms running right now, like in today's world, right? And then let's see how many parameters they are using. Very, very important, right? Now, if you look at the chat GPT, I believe many of you have used before.
Affiliates best friend.
So the chat GPT is a form of machine learning. It's called LLM. It means what?
That one is going to answer
You're going to ask them.
answer the LLM.
So the chat GPT is a form of LLM, large language model, right? It's just one form of machine learning, right? And then uh, it, it started from somewhere, right? So now in machine learning, right? In other, we are looking at how accurate your algorithm is. Accuracy is very important, right? Because you want to know that you want your algorithm to be as accurate as possible. But there's an issue. To make your algorithm as accurate as possible, you need to enlarge your parameters. You need a lot of a lot of parameters to make your model very, very accurate. So now if you check, the first chat GPT came in around probably 2000 and 2018 or something like that. So on your on the y-axis is the number of parameters. As I said, the wi, the weight, and the biases, right, are the parameters. So how many parameters were there? You see that it's in the number of parameters is in millions, right? It's in millions. this artist. It's millions, right? So now in 2018, the chat GPT one also, or just chat GPT was using about one, probably 1 million parameters around uh, uh, around that range in 2018, right? And then that one wasn't really that accurate because at least they were actually trying to begin, right? But now with the chat, I think now they have chat GPT-4, right?
Yeah.
So now imagine, now we have chat GPT-3. How many years ago? From 2018 to what? 2023, right? That chat GPT came out. Now they see the increase in the number of parameters. The parameters have increased to about almost 200,000 million parameters, right? So many parameters. And then chat, and then this one is very, very accurate. It's very accurate. And then now we have four, right? ChatGPT 4. Probably the number of parameters has doubled. So to make a machine learning model accurate, the number of parameters must increase all the time. But it means that we have an issue here. So how do you run something like this with so many parameters on our embedded device that has only 1 megabyte? You see that we have an issue, right?
Then
Because you see that,
four ChatGPT four is 1.76 trillion.
so you see how large it is. So many parameters, so many parameters. Now, the important thing is that a parameter is stored in memory. So if you check our biases and our weights, right? Why it cannot fit into small devices that these are, so if you take my weight and then my bias, it's a value, right? It's a value. It must be stored in memory. A value stores, you must store that value in memory and then access that memory to use it. So if, let's say, you use floating point numbers, you know what floating point numbers are? Floating point numbers, you guys know what they are, right? You know,
Decimals.
you know decimal numbers, you know integers, floating point and stuff like that. Like probably 3.4 times 10 to the power something. That's some kind of floating point number. It has some kind of decimal point and stuff like that. So if you use, let's say, floating point, and then we write something like 32, right? What does this mean? Or just simply, right? If I write something like int a, this int, right? Int a means that I'm creating some kind of memory, and then the value of a will be stored in that memory. So if I write int, right, how much memory am I using? You know that this int is called a data type, right?
Yeah.
You know, in programming. So once you write something like int a, you have created a memory for it, and then the memory has a size. So if I say int, what does that mean? How many? What is the size? Int a, int a. Once you write your C programming, C++, your Java, whatever, you encounter stuff like this. Int a, you write int a, then whatever, right? Right? So, huh? So if I write int a, just int a, what is the size of the memory I've created to store that value?
I have no idea.
How many of you program here? How many of you program? Nobody.
So now it's C++, Python, Python.
When I read C or
So now we use
I
Python to use C.
I did it.
Nobody programs here.
Oh, we did it.
Huh?
Next one activities.
Java they doing PLC programming, not
Yeah, but still, like you write,
that one is ladder logic and
no, but you create memories for variables. You write variables, so it's the same thing. Programming, just basics of programming, no, right? So once I write, as I said, you have so many data types. The int is it's just one data type. We have int, and then somehow a data type of 32. You can write int 8. A data type of what? 8. You can write float. Float has a data type of 32, depending on your machine. Right? So now wait. It means that if I have my weights, my W and then my B, and then I'm storing this W and B as a probably int. Int normally is what? 32-bit weight. So I've created memory, right? And then the memory location is from 0 to 31. And then I'm storing this value inside there. So I've created a 32-bit memory, right? 32-bit memory for just storing one. So now imagine if I'm storing millions of them. So just let's say if I have about let's say 1,000 weights W, right? So I'm storing 1,000 times 32 bits, right? So that's about 32,000 bits of memory I need to store just 1,000 weights. But you know that for the chat GPT, what 3, I have about 200,000 million of. So imagine the amount of memory you need to store that. Memory. You need to store that. And then we have the weight, the W, we have the biases. All of them have different data types. So it means that the memory is so huge, right? That's just the main point. So how do we scale this memory to fit into a small device like that? That's what you're going to learn, right? And now it's not only memory that you have to consider. You have to consider computation, how fast the operation run or how fast your algorithm run, right? And then in machine learning, we use something called we use what is called the flops to measure how fast your algorithm is running. The flop just means floating point, the one that will floating point operations per second. So in the exams, just something like that. What is floss? I talk exam without Charlie. Chairman just spoke up. Operations per second. So that's how you measure how fast they're going. Floating point. So it means that the floating point operation is doing some kind of decimal calculations, right? So we have floating point operations per second. So that's how you measure your machine learning algorithm, right? And then we see that from probably from 1960, it started the first machine learning or the first kind of anything that was doing any form of machine learning started from 1960. So we see that from 1960 to about 2020, the number of floating point operations per second is for each algorithm that is designed. All of these are algorithm design are just increasing. So you can see from the graph, it's just increasing, right? So the number of computations are just increasing just like that. So how do we scale these computations, or how do we scale it down to be able to run on the our embedded board, right? That's another issue, right? So we have an issue of memory, right? And we have an issue of what the computations, right? So now, just because of that, I think I talked about this before. Just because of uh, how much time it takes to run a machine learning algorithm, some some other industries are creating their own kind of machine learning hardware. And then I talked about what is a TPU, right? The TPUs are created by I think Google. So they are creating their own hardware to run just machine learning, right? So they create this CPU and then they pack a lot of them, right, together into a data center. And then I said that the last time that these data centers are located around the seashore and stuff like that, around water bodies, just because they consume a lot of power that they heat up. So if we don't locate them in a place where it is cool, then probably one day everything will just blow up. So they locate these data centers around the sea and stuff like that. So how do we compress all of this, right, into our tiny machine learning board like? So we have a big issue to solve, right? Now, and these are all of these are machine learning algorithms that has been developed over the years. And then on the on the on the y-axis is what is called the accuracy. As I said, each machine learning algorithm you need to measure the accuracy. You need to measure the accuracy, right? How accurate is your algorithm? It's very very important, right? It is one of the most important things in machine learning. How accurate is your machine learning algorithm, right? So now, if you look at the boxes here, the round things, right, how many parameters each machine learning algorithm has, right? And then your x-axis gives you your flops, the floating point operation per second, how long it takes to run that algorithm. So all of these are just algorithms, right? And then one of the first machine learning algorithms was called AlexNet. It was developed in 2012, right? Now, what they did was that there was a competition, right, designed by some school like that. And then what they did was that they actually grouped images into categories. So they had images. So they had images. So they had a folder that has images of, let's say, airplanes, right? They had a folder that had so many airplanes, so many different types of airplanes, right? They have a folder that has, I think, apples, right? So many apples. They have a folder with cats, a folder with dogs, and so many folders, right? So they asked people that how are you going to design an algorithm that will classify these ones, an airplane, a dog, that will train, that will use this data here to train the algorithm, and then after that, after 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 I'm wondering, what any issue? Huh? Hey,
So you want to stand at the back.
so let me finish this one, and you can just go and straight.
So let's go.
So as I said, they created these folders, and then they said design an algorithm that will classify the airplanes apples accurately. Like, so how accurate can your algorithm be? Right. So people designed so many algorithms, right? And then the algorithm that won that competition was the AlexNet in 2012, and then the AlexNet had an accuracy of 57.1%. In 2012, and then the size of the model they created was 61 megabytes in size. Right? So this is not in today's world, we are looking for accuracy of about 90%. If not, nobody will mind you. If you design an algorithm with accuracy of 57%, you have failed. Like, your algorithm is not really that accurate, right? Now imagine if it was a medical device with an accuracy of 57%, then nobody will even. But the size was 61 megabytes. Now, the next one, also the same classification, came in about 2014, about 2 years later. Some people also designed an algorithm known as the VGGNet. The accuracy for that one increased to what? 71.5%. That's actually good, right? But look at the size of the model. So it means that it has increased from 61 megabytes to, right? So it means that we have an issue here. We don't only want you don't only want to design an algorithm that is accurate, but you want to design an algorithm that uses smaller size. That's now very important nowadays, because you want to run your algorithms on embedded devices, right? So now, one of them also came called ResNet. I think 1 year later, it's called ResNet. It had an accuracy of 75.8%, but the size reduced. So now from this one, the size was 5 to 8, right? Now the size has reduced, and then the accuracy too has increased. So that's very good, right?
Yeah.
And then another one also came. Now they wanted to design algorithms for the phones. So one came called MobileNet V1. Look at the accuracy, 70.6% accurate. The size reduced. But you see that the accuracy has reduced from ResNet. The accuracy has actually reduced. But the size has also reduced. Right?
That's it. It's still the same year.
Yeah, yeah, yeah. So from 2012, everybody was just designing. They saw that machine learning was not becoming something that was possible. Everybody was now designing. Everybody was trying to design, right? So now this one, the mobile net was actually for phones, compressed to fit in. Because if you have 60 megabytes of size, you see that your phones right now they have RAMs of like 5.2 megabytes and stuff like that, right? Some of them are even bigger, right? Your phone, so you can easily run this one on your phone, right?
Yeah.
With 60 megabytes. That's no issue. But now we have an issue here still. How do we run this mobile and V1, which has 60 megabytes on our device that has only 1 megabyte? So you see that still we have an issue. So we need to go further and develop algorithms that uses less than 1 megabyte of memory. Right? So how do we go about that? Now we now have to start thinking about the machine learning models itself and some techniques to actually use to scale down the machine learning, the machine learning algorithm itself. And then we have so many techniques to actually reduce the size of your model. One is called pruning, and one is called quantization. That's what we're going to look at mostly. You know what pruning is? Just the English word pruning.
Yeah, yeah.
What does it mean?
So you try to take off the unwanted parts.
Yeah. So look at this here. So this is how the algorithm look like in real life. You have neurons and then you have interconnections. So you can see interconnections, right? Now, as I said, all of these interconnections here, those interconnections have weight. W1, W2, W3, right? Right?
Yes,
So
sir.
you see that I said, I think the last time that the first layer is the input layer. The layer within
Meaning,
the layer after the input layer, these two layers, is called the hidden layer. And then this layer is called the output layer. Right? So between them, all the lines you see have a weight. And then all of these neurons also have the bias. Right? So how do you scale this one down? You can just easily scale or reduce the size of this one by reducing the weight. So how do you reduce the weight? By removing some of the lines. So if I remove some of the lines here, you can see that once you remove some of the lines, your model becomes smaller. It uses less weight, right? But there's an issue here. Once you remove some of the interconnections, the accuracy might reduce or not. So what you do is that you design a model that is big, right? And then you begin to remove some interconnections, and then you test the accuracy to see whether it fits into your system. So you want a system that is smaller size, but the accuracy too must be probably not as high as the original one. Of course, you can't get the original one, right? But as close. So if the original one, this one has an accuracy of, let's say, 80%, right? You should be targeting an accuracy of 78% by reducing. So it shouldn't go below some number. Right? So once you remove the interconnections, you are reducing the size. Right? This
yes,
is right. And then this one, if once you remove the lines, both interconnections, we call it synapses pruning. Each line is called a snap. So once you remove the lines, you are doing what is called synapses pruning.
that if you remove the line, meaning the accuracy will come down.
Yeah, yeah, yeah.
Since
Now, eh?
the size will come down, accuracy will
Yeah, the accuracy will come down normally. And then you can also remove the neuron. So the neuron, inside the neuron is what the calculations actually occur, right? The f is sum of x1 times then everything occur within the neuron. So you can also remove the neuron to
Calculation function.
eh?
Calculation function.
Yeah, so you can remove some of the neurons to reduce the size. Once you remove a neuron, the size are reduced. But again, the accuracy too is affected. So you must be careful how you do it. Understood?
Yes.
So that is then as we have another one. So that is just one technique. The technique I just talked about is pruning. The next technique is what? Quantization. Have you heard of it before?
Yes, yes.
What does it mean? Quantization.
So that one we did it in the Ghana first semester.
So so as I said,
Talk about sampling.
so if I take a if I take a typical number, like okay, let's say I have a four-base number, right?
Yes.
This is how a four-base number looks like. We have I've created memory location for the four-base. So this is memory location 1, 2, 3, 4. Each location stores 1 bit, right? So this is it stores 1 bit. So if I'm saying a location stores 1 bit, it means it can store a 0 or a 1. 0, 1, you know what that is already. So if I take this 4 bits, right, and then I say that I want to scale this one a, to a 2-bit kind of number. So I don't have enough memory. So I have a 4-bit number, but I want to scale it to a 2-bit number. I want to store this 4-bit number into a 2-bit memory locations, right? How do I do that? How do I do that? Yeah, so yeah, so how does it how does it actually work? So if I have a 4-bit number, right, the lowest number will be what? So 0, 0, 0, 0. The lowest number in a 4-bit number is 0, right? The highest number in a 4-bit number is what?
Wow, wow, wow.
Hey, wow, wow. The highest number in a 4-bit number is 1, 1, 1, 1. Right? So if I convert this is binary. So if I convert this to decimal, what is it?
So you should do the calculation.
Okay, yeah, it doesn't matter. It's F or 15. So it means that a 4-bit number can store 0, 1, 2, 3, 4 up to 15 decimal numbers. 0 to 15. Now, a 2-bit number can store how many? The least number a 2-bit number can store is 0, 0. So it's also 0, right? Right?
Yes.
The highest number you can store is what? 1, 1. 1, 1 is what? In decimal, 1, 1.
0, 1.
It's 3. So it means that a 2-bit location, the 2 bits can store 0, 1, 2, 3, right? So now, what do I do? So now, I take this is 1, 2, 3, 4. I have 4 numbers here. I take 4, and then I take this is how many? 1, 2, 3, up to 15. So it's what? It's 16. I take 4 divided by 16 is what?
Up for
4. So I make a rule that the first 4, 0, 1, 2, 3, is 0. Understood? The next 4 is 1. So anywhere it sees 0, 1, 0, 1, 2, or 3, it just labels it or it stores the number 0. So in doing this, it means that I've reduced the size from 4 bits to 2 bits. But if I do that, it means that there will be some kind of error margins, right? But that one don't matter here. But the main point is that this is how you do in machine learning to reduce the size. So you take a weight. If your weight is 4 bits, you quantize it into a 2-bit number, right? And then again, it will affect the accuracy, as you know, right? So all of this,
when it's 16, you can compress it.
pardon?
When it's 16,
Yeah, you can also compress it too. That. So that is what quantization is. Just taking your data type, which is bigger, and making it smaller. If you do that, the accuracy is affected. Understood?
yes.
Okay. So now our next is the runtime, right?
Okay, so how about the knowledge?
Now that one is what we are doing. We don't really need it. So
Okay, same machine learning, accuracy is important.
yeah,
Yeah, so if you are going to do the same, then it's going to affect the accuracy.
yeah.
How do you do it?
So now the accuracy is important, but it has to be able to run on the embedded device also. Understood?
Come again.
We are designing for an embedded device that has limited
Space.
memory,
Yeah,
right? So accuracy is important, yes. But what is also important is the size. So both the accuracy and the size is important. So what you normally do is that those once you tune or you quantize your model, it won't be as accurate as the original model. But as I said, if the original model accuracy was about 80%, you are supposed to be targeting an accuracy of about 78%, and that will be fine. If you're able to, if your original model has 80% and then it uses so much resources, and then you're able to do some techniques that will bring it down, and then uses the accuracy change to something, it's still okay, and then they can run on an embedded device, it's still okay. But it shouldn't go below some kind of accuracy, right? It should be as close as possible to the original one, right? So it means that you are using different techniques. You can do only pruning, you can do only quantization, you can do both pruning and quantization to reduce the size. And then once you're reducing the size, you are checking the accuracy. And then so you know how accurate you want your system to be, right? You know. So probably I want a system that is 80%. So I'm targeting that. So I'll be reducing to try to get to that accuracy. And then I say, okay, this one is fine. Understood? So now we know the algorithms, but how do they run, right? So they use what is called the runtimes, like some kind of frameworks to run the algorithms. And then one of the frameworks we use to run the machine learning algorithms is actually the TensorFlow. Have you heard it before?
Yes, yes.
Where?
Yeah.
Seriously? Only here? Okay, so we have the TensorFlow framework. It's like a software library that is used to design and then to train machine learning algorithms and sometimes to deploy machine learning algorithms. It's called TensorFlow. And then it normally runs on the TPUs and stuff like that, right? But then if you're using TensorFlow runs on CPUs, GPUs, TPUs, right? It's a very huge library, very, very huge because it contains a lot of stuff for you to be able to do an entire machine learning, right? So what if you want to run it on an embedded device like your phone? You know that your phone consumes less memory than your GPU, right? It consumes less power, and then it is only for okay now. So it only focus on inference. Who knows what inference is? I mean, from the English word,
Freedom
huh?
and command girls.
It's just an English word. So what is inference?
That's is it the English meaning of inference?
What? Inference
So
to invoke something.
hmm?
Inference to invoke.
Probably. So now, so if we take the TensorFlow framework, right, what it does, if you look at the machine learning pipeline, right, I think I mentioned before that you have to first of all design your model. So you design your model like how those ones, right, with interconnections, right. You design your model and then you what? Train your model, right? Now, after you train your model, you test your model. And after testing and everything has gone well, you deploy your model. Deploy. You deploy your model. Easy, right? So you design your model, you train it, you test it, and then you deploy. The deploying just means that you are designing some kind of application for it, and then it should run on, let's say, probably your machine. So now, once you design your model and then you train it, and then you deploy it, you can't train anymore.
Yeah. After the training, where do we place validation on?
Oh yeah, there is training and validation.
Okay.
Training and validation. So you are training while you are validating it. And after that, you test it, and then and then you deploy it. So as I said, once you've done, so you go through these steps. This these steps from the model design to the testing. You go through it so many times so that it fits or it meets your kind of accuracy. Let's just say accuracy. It meets your accuracy. Then after that, you deploy it. Once you deploy your your model onto any device, you cannot train on the device anymore. All you are doing is inferring. So what that means is that if I have images of cat and dogs, right? I use these images to train. I design my model. I use those images to train my model. Then I test my model. Then after that, I deploy. Now, after I've deployed, all I'm doing is that I give it a picture, and then it tells me whether it's a cat or a dog, right? So now that picture I'm giving it, it doesn't use that picture for training anymore. It's just telling me it's a cat or a dog. So the training means that the model is learning, right? So you learn so many things. Then after that, once is it's like here, right? Right now, you are learning about machine learning, right? Right now, probably you don't know anything about machine learning, right? So you need so much resources, and then you need so much time to learn about machine learning. So you will learn and learn and learn and learn. And then after that, if I ask you any question on machine learning, you don't have to go and open your books anymore. You just give me the answer. So it means that you have learned enough that you don't really need to go and learn again when you are asked to produce something.
Okay, test.
That no, no. I mean all of this because you learn. Let's say you let's say you learn and then you test yourself, right? So you learn and then you go through some questions and then you answer them, and then if you don't get some correct, you go back again and go and learn again and come and write the same test again, right? And then you do that so many times, and after that you become an expert. And then right now I give you a question, you just give me the answer. That's how machine learning also works, right?
So
So it means
how
that
compiling, how where does it?
everything falls here.
Okay.
Understood? So now it means that, as I said, once you deploy the model, what you're doing is inferring. So if I design a machine learning model, if I'm designing, I'm using the TensorFlow, and then if I deploy it on the phone, I don't take a picture or something like that, and then I want the phone to learn again. The phone doesn't have enough resources to learn anything, right? So all it does is that it just takes the picture, it passed the picture through the algorithm that I've already developed, and then it has already learned. And then it gives me some results. That's all. So on embedded devices like the phone, you are only doing inference, right? The inference just means that I give it a picture, whatever, then it gives me the results. It doesn't learn, it doesn't train. So it means that I've done the training elsewhere already, and then I've deployed it on the phone. Understood? So if you want to deploy on the phone, we need another framework, a smaller one, to run on the phone. We need what is called the TensorFlow Lite. Have you seen it? TensorFlow Lite. That is small enough to run on phones. The TensorFlow framework is too big to run on phones. So use the TensorFlow Lite framework to run on the phone. Right? So it means that we have these two frameworks, the TensorFlow and then the TensorFlow Lite, right? And then we obviously have some kind of differences between the two, right? The TensorFlow framework is used by machine learning researchers mostly, right? So if you are a researcher, you want to design a model. So you start from the scratch. I want to design a model. So I'm looking at how I'm going to design a model and test the model accuracy and stuff like that. Those are the people that use the TensorFlow model. And then the people who use the TensorFlow Lite model are the application developers. So they are using an already trained model. The model is already there. They just take it and then they just design an application for it, right? So the TensorFlow model need a lot of resources to run, but the TensorFlow Lite model needs less resources. Understood? Understood?
Yes, yes.
So in actual fact, or to run it on like to run to run a machine learning algorithm on your phones, all you do is that you have to train the model using TensorFlow, right? And then you use TensorFlow, what is called a TensorFlow Lite converter, to convert that model into TensorFlow Lite kind of architecture. And then the TensorFlow Lite model has an extension of the TF Lite. So if you see any model or any design that ends with dot TF Lite, it has been converted into a TensorFlow Lite model. So once you use a TensorFlow Lite converter, what it does is that it does your pruning and then your quantization for you. So you choose it. I want to do pruning or quantization, right? Then after that, it gives you a very small model. That would be .tf Lite, and then you can easily deploy that on your phones or your iOS and stuff like that. But then a model that can run on a phone does not mean that it can run on the embedded system, right? Because the embedded system is still smaller than your phone, right? So normally you use the TensorFlow to train the model. So this is the pipeline of most machine learning stuff, right? You use the TensorFlow model from the beginning to train a model, and then you do what? You convert the model, you optimize the model, and then you deploy the model. You do all of this, and then you make inference like that, and then you do all of this using the TensorFlow Lite library, right?
Okay.
Okay, so now probably there are some kind of the hardwares are specific. The CPUs on your microcontrollers are actually also specific, right? We have, you know, the ARM makes CPUs, right? ARM. You guys know that it's a company that makes CPUs, and then they make CPUs for different types of applications, right? They have what is known as the M series, M0 plus, M0, M3, M4, and then they have the R series, they have the A series. And then all of these depend on the kind of applications that are going to be run, right? So if we take the M1, the M0, M1, whatever, those are made for microcontrollers, right? And then we have some for real-time processing, which are the R4 and stuff like that. And then we have one for actually heavy applications. That is A5 and A4. So now, once we come down, the microcontrollers consume less power. We already know that. But the complexity of those designs too is that the microcontrollers are very, very simple. They can run a lot of tasks, right? So probably, so here the microcontrollers to have some kind of functions. Each of them has the kind of functions. They have some that can do general processing. They have the, so you see that the M0 they can do general processing, very, very simple tasks. Then we have the M3 that can do data processing and stuff like that. And then we have some that can do DSP operation. You know what DSP is? Eh?
Digital signal processing.
Processor, you can do DSP, and then we have some that can do FPU, floating point operations.
You say
FPU, point operation. So with that said, we have seen some challenges and stuff with our tiny machine learning course, right?
yes, sir.
Any question?